Our next speaker will be Kyle Stanish, who co-authored this presentation with Dan Moser, both out of Klein and Hoffman. Kyle is one of the major contributors to the 364 document. Kyle's a senior associate too at Klein and Hoffman in Chicago. And Kyle's going to speak to us today on assessment and repair of precast parking deck with construction defects. Kyle?
All right. Thank you, Paul. I just really want to, before I get started, really acknowledge my co-author, Dan Moser. I actually did this work while I was with a company previous to where I am now at Walker Consultants. So I want to acknowledge their allowed me to present this work for them, and I also want to acknowledge the work not only that Dan did, but my other people in my team who worked on it. And I probably have to say that particularly because two of them are sitting in the back of the audience, Bill and Diego, so I can't ignore them. They're here to catch me out. So I'm going to change direction a little bit before what Ben and Ashok did. Ashok was talking about the document as a whole, and Ben was talking about a specific chapter. What I'm going to be doing is taking a project that I did that I really used the techniques and the concepts and the plan that this document has developed, kind of how it applies and how it works to a specific project. So really the way this started, there's this precast parking structure, not a huge structure, 2 supported levels, 3 bays wide, so it's about 200 or so, 150 to 200 cars, so not a big structure. Constructed at field top double T's, central bay is the ramp. It's about 7-year-old. There's really nothing remarkable. You see thousands of these, across the country. It was in Illinois, so subjected to fairly significant environmental conditions, but it was only 7 years old, so they weren't expecting any deterioration from chlorides or corrosion or that kind of thing at this point. But what happened, and that's just an overall picture, so that's kind of a plan of what it looks like. There's a picture looking up one of the ramps. Again, nothing remarkable about it. You see thousands of these being built everywhere. But one day what happened, I was walking along and they saw this crack, and they didn't have the shoring at this time. It was just the crack that kind of developed in the middle of one of the double T stems. And it was a fairly severe crack. It was varied in dimension from over its height, but the base of the crack was about 3/8 of an inch wide. So that's not one you'd normally expect, particularly in a pre-stressed double T. So owner kind of like, what's going on? We need to figure this out. And that's when they kind of started calling us in to have a look at it and really work through the assessment. And this is the procedure. I think Ashok threw this chart around, and this is the procedure that's outlined in the 364.1 document for doing assessment. And it's got a lot of things in there and a lot of iterations and things going back. But what I really like about this document, and what I think one of the strengths of it, is it does outline a number of steps that you need to go through and that you need to think about when you put together your assessment plan, when you're starting talking to your client and figuring out what are you going to do. So there's a lot of iterations here, a lot of small different text. So in my mind, I almost want to more break it down into these 5 different parts. And they're not, I'm going to talk about them linearly. They're shown linearly as if you do one and then the other. But in reality, it does become an iterative process, kind of do things. You figure something out and you go, oh, I need to check this. Oh, based upon this information, I need to go back to the plans and look into that kind of information. So I want to talk about it as if everything was magic and I did this and I did this and I did this. But realize that's an oversimplification of how things are happening. But if you think about these 5 things and you kind of run them through in your mind, that helps you to do kind of a complete assessment. So the first one we did, or the first one I'm going to talk about, is document review. So for this, as I said, it's a precast parking garage, only about 7 years old. The owner had a fairly good documentation of what was going on. So that's not something that's always the case. That you can always get design drawings, you can always get shop drawings, but we were able to get all of these information. So we were able to have a good look at the architectural drawings, the structural drawings, the precast shop drawings and details that were provided, as well as the design calculations. So we had a fairly good set of information to start with to try to figure out what the heck developing. And one of the key things that we did in this that was very useful in the review was compared the calculations to the shop drawings. So we looked at the loads. Yes, the loads are correct. They did design them for the right loads. We were able to compare the drawing requirements that were on the structural drawings to what were done in the calculations by the precaster, and yes, that looked okay. We looked at the span, the depth, the width requirements. They all kind of met. So the calculations seemed to be pretty fine for what we were doing. They kind of made sense to what the structural drawings were requiring. We were able to, like I said, it had a really great advantage. We were able to get piece drawings for each member, and we could compare those drawings to the calculations. And overall dimensions, yep, they agreed with what we're showing on the structural drawing. Concrete strength that were called out in the calculations, yep, that's what they were on the structural drawings, on the calculations that were used by the structural engineer for the precaster, yeah, that's what was being called out on the precast shop drawings. Number of tendons that the calculations were showing, yeah, that agreed to it. But then we kind of hit this thing, and that was kind of interesting. And obviously, it's kind of like our eureka moment when we came across this. The calculations were using 0.6 diameter tendons, while the shop drawings were using 0.5 diameter tendons. That's kind of a little bit different. You can't use smaller tendon for a bigger tendon and expect it to act the same way. What's 0.1 of an inch? Well, if you do the math and the relative size, tendons are 83% of the size of the 0.6 diameter tendons. So you're really, oversimplification, but you're at 83% of what the strength of what it's supposed to be. So kind of right in the shop drawing phase, or in the initial document review phase, we kind of found something that said, yeah, hey, this is something we need to look into further. Which is nice. You don't always see that. Usually it takes a little bit. It's a lot more complicated than that. But no, that wasn't the end of an issue. We have the shop drawings that we were provided, and we have these calculations. Well, we need to know, how does that relate to the behavior of the structure? So we needed to come back in, and we still did the field investigation and testing and all this thing. So talking about the field investigation a little bit, one of the most important things, we're dealing with cracks. We need to document what was the nature of the cracks. So we not only documented the primary crack, I'm going to call it, the one that kind of started all this thing that was kind of a big flaring issue. We figured out we documented where it was on the double T. We talked about its width and how it changed with height. We looked at how high it was and if it was different from one side or the other, trying to just get this crack is kind of something that's causing everything to happen. We need to know as much as we can. So just doing that type of information in depth on this one crack was very important. But we didn't stop there in terms of the assessment of the structure. We have something else going on elsewhere that we should be seeing, because did they, if we go back to our cause, if we have 0.5 versus 0.6 diameter tendons, why is it only happening? Is it only happening in this one T, or is it something that widespread? If the shop drawings were showing one thing, then we think it to be widespread. So we did do a visual exam of basically the rest of the structure, and we kind of documented what we saw, and we were able to find other cracks. So, but they were, I don't know how well you can see those on the screen. It's always a challenge when you're showing pictures of cracks in the presentation. But they did have hairline cracking of the other T stems, and when we documented it, the nature was different from this primary crack. And instead of having one big crack, there was a lot of smaller cracks that were kind of spread along the length of the stem, but they were still present, and which kind of was good information to know that this may not be something that's going on just this one T stem, but it's something that's a little bit more widely spread. And then I don't know whether this fits, but as part of the investigation, because we knew that the size of the tendons were potentially part of the problem, we did do a an opening, and we did expose one of the tendons, and we were able to visually confirm that, yes, they use half-inch diameter tendons. This wasn't something that was found, that was caught somewhere along the line, so we're going down this rabbit hole, and they actually, you know, they may said 0.5 in their precast shop drawings, but they used 0.6. No, we were able to get in there and expose a tendon and confirm what we found in the shop drawings, that 0.5 inch diameter tendons were being used. So that's kind of one of the things that you really should be doing, is kind of take all this information, kind of relate it one into the other. So our shop drawing review, our document review informed what we did in the field investigation. So we were able, so once we found that out, we included in our field investigation looking at what the size of the tendons were. We did a bunch of other field work too, not as relevant, so I'm not going to really get into it. You know, we did visual review of the rest of the structure, made sure nothing else was going on. We did some chain dragging, make sure, you know, it wasn't, you know, we weren't having widespread delamination, deterioration. We confirmed some dimensions of the structure that, you know, of the members, that they all seemed to work out. And we did examine the T-to-T connections. We did a bunch of other stuff as well. Remember, this is only a half-hour presentation. You're getting the highlights. But we really, you know, so we didn't just do, but why I wanted to bring this up was because you don't want to get blinders on, find something and go down that rabbit hole and assume we know the answer. We want to make sure we have enough information to kind of confirm that, hey, it's not anything else. There's not, you know, other things going on, which, well, this case, it was getting ahead, it was fairly straightforward. More often than not, you really have a lot of different things going on, and that's what's causing your issues. After we did our field investigation, well, time-wise, kind of simultaneously, but we also did do some testing. We didn't do all the tests that Ben talked about. We really were focused on these three. These are more related to what the structural condition was, because we weren't worried about deterioration at that point. We didn't see anything. We didn't find any significant delamination. We didn't see a lot of corrosion and so forth. So we were really focused on these three tests. Compressive stress testing wasn't super exciting. Kind of found that, yes, it was what it's supposed to be, so it's not really a concrete strength issue. So not super exciting, but good to know. Bond pull-off test, so it was a field top system, so we have that concrete overlay over the top of all the double T's. We did found that, yes, it was generally well adhered, so that wasn't really an issue with something like that. But GPR was the one that was most important for what we found, and that helped us confirm that they didn't do something like, okay, we only used half-inch diameter tendons, but we used more of them to make it up. They did match, you know, what we found, the dimensions and the locations of the steel and the tendons and how it was laid out, matched what were the shop drawings. GPR doesn't tell you the size of the tendons, which why we had to do the opening, but it was able to confirm that, yes, except for this potential issue with tendon size, it did match what was going on and what was expected. So that was very useful in its way. So this is just the layout from the GPR. So after now, we go to the evaluation, which is kind of the pulling everything together. We take all the information that we found, and we did primarily looking at it as a structural evaluation. So we went back and we didn't just rely on what the structural engineer was calling out as the required load requirements. We checked them to make sure that, yes, they agreed with what the code requirements were. Very simple, fairly basic, but important first step. And then we took that and we calculated, you know, what were the applied loads, what should they be resisting, what should they design for, kind of separate from what they were called out and what was done by the precast design engineer based on the requirements. And then we calculated the capacities, and what we did, based upon our knowledge that there was 2 tendon sizes potentially being used or potentially being considered, we ran the numbers both with 0.6 diameter tendons and 0.5 diameter tendons, and what we found was we agreed with the precast engineer who did the calculations that 0.6 inch strands were fine. They met the code requirement factors of safety. The 0.5 inch diameter tendons did not meet those kind of things. So not surprising, you use smaller tendons, they're not strong enough. You wouldn't have used 0.6 if you didn't need them. So that kind of was great, that kind of all fit out, and then we were able to take our results and did reporting. Great. So yeah, and I'm not going to talk about a report. A report is just a bunch of pieces of papers, but we have, but that was an important step in communicating it to the owner. Just to conclude that, we had an exterior post-tension double T, FRP strengthening. So what we ended up doing, we took that one with the double T, and then that one we did exterior, and then we did FRP strengthening of the rest of the remaining double Ts that had all that cracks. And just because I'm an engineer and I like these, even though it's nothing to do with the assessment, I do have some pictures of the repairs. So I have a couple minutes left that I can quickly run through them, I hope, Paul. This is a kind of a couple of pictures of the repairs of the exterior post-tension you can kind of put in. See, it takes a little bit. You've got the kind of bars to make it continuous, you can't see them. See my mode. So you can see, you have a number of bars, kind of make it composite. There are, I don't know how well you can see those. You see them a little better in the next picture. But there are tendons, draped tendons that run one from the other. This is kind of another picture, maybe a little better picture showing where the tendons are located, trying to really restore. And the idea was, the way we worked this was we weren't no longer, because of the width of the crack and the deflections that we saw, we weren't going to rely on the original tendons. We actually, so as to not overload this, after we shored the double T, we cut the original tendons to make sure that they weren't doing anything, because we don't want to get too much uplift when we add our exterior post-tensioning. But we went in and redesigned everything so that the post-tensioning there will take care of the load, basically replacing the tendons. Because of the exterior post-tension, instead of the straight ones, we did draped ones and a few things like that. But that's kind of where we ended up. So you kind of see the tendons, you see the formwork. Here's kind of a picture. On the right is for the concrete place. The left is how they're placed. We left a little bit at the end to allow us to stress them, and then poured the concrete, stressed them, and this is the kind of pictures at the end, kind of what it looks like. You kind of see, don't know how well you can see that, but you can see the second pour to encapsulate the tendons, and really what we ended up with was a wider double T stem at the end. So that's what we did for the main one, and then running real quick. Here's for all the other ones. The first step was injecting the cracks, kind of repairing the cracks, making sure they're not going to be an ongoing issue, and then adding FRP. As you can see, it was basically every T-stem that we needed to add the FRP, so there's a fair amount of it. On the right, we did do confirmation quality control testing, taking some samples from the end of the FRP, doing bond pull-up testing, make sure that the prep was fine and the application was fine, confirm that it worked, but we wanted them to be located at the end, so it's not really affecting the main strength of the FRP. And to make everything kind of hidden, we coated everything so that you don't walk in there, you don't see all those big black ugly FRP systems. I know some people love it, if you're an FRP manufacturer, it's music to your ears, but most people, you want to kind of hide what the FRP looks like. So that's kind of quick overview. I think, talking about an assessment, these are my big 5 things that we need to think of. That's certainly reflected in the document. I think if you go through these as a mind through your checklist as you set up your assessment, kind of definitely covered what can be done. You may not need to do all of them for a specific project, but it certainly helps you getting on in that direction. And following that assessment process improves your quality and completeness of the assessment, kind of understanding what's going on. Thank you very much. Any questions? You have a few minutes for questions, or? Yeah.
Let me pull this over for you.
Sure. Yes.
My question is, given the load and resistance factors that are used in design. What was your conclusion as to the cause of the cracks? Was it simple overstraining in the tendons?
Yes, when we ran through our calculations, it was definitely over the crack, even including the pre-stress force that was there. So it was in that kind of intermediate range, and that's definitely a concern, particularly for parking structures. That once you start cracking, these are designed specifically to be crack free to avoid durability issues down the line. So we wanted to address that, but also it just didn't meet the code required factors of safety. But when we did it without looking at it as an assessment viewpoint, it was in that range, below the ultimate, but above the cracking load of the structure.
Thank you.
Yes.
I wonder why didn't you make a load test, let's say, instead of this analytical method? And if it passes, that's it. Could it be possible to do the loading test in this case?
Well, loading test is always possible if it's something you wanted to do.
Instead of doing the whole rehabilitation by just relying on analytical method.
Part of the issue was we were already seeing the stress that we didn't like, that we didn't want to keep going. It was all, we had that one that had, if not failed in the sense that it collapsed, it definitely is beyond what you would expect in its performance. So we definitely needed to address that one, no matter what the results of the load test were, because we did have an exposed tendon. And the other locations, it was, we had something that was already cracking. It was already something that was not performing correctly. And once you get into the cost of the repairs versus the cost of the test in this situation, given the amount, it's a lot more comparable than I think you're maybe thinking. FRP is fairly inexpensive to get it done, and the owner wanted something to address these issues that were developing. So it wasn't something like, even if we load tested it, we weren't going to, and it's fine, we weren't going to be walking away from it anyway. We needed to address some of the cracks from a durability viewpoint, if not from a structural viewpoint.
Thanks.
Right. Great. Thank you very much.
Thank you, Kyle.